I will move us on now to our lightning talk. So we've got 4 lightning talks. If you were here earlier, you already know the drill. If not, 4 lightning talks, and then we will head into breakout rooms. You can choose which breakout room you want to go into. You can move around between the breakout rooms, and we will share our screen telling you who's going to be where. But I will start us off with Ray. So Ray, the floor is yours.
Hi, thank you, Sammy. Just sharing my screen now. Is it showing?
It's thinking, yeah, that's coming through.
Okay, thank you. Right, hi everyone. My name is Ray and I'm a senior business analyst at the Royal United Hospital in Bath. And today I'm going to just briefly talk to you about the acute ward bed occupancy simulator that I've built recently. So this a common challenge in most, if not all, of the acute trusts currently is a high demand for bed spaces on acute wards. And we often find decision makers trying to see if they could discharge patients earlier from the wards or have maybe an extra bed or 2 on the wards to try and counter those problems. But we don't actually know exactly what impact we will have by doing those changes. So this simulator is basically trying to give us a better picture of the impact itself if we make those changes. So this discrete event simulator, like I said, is a very simple bed occupancy simulator on an acute ward. And the features that it has is includes the variable arrival rate every hour, because we know that in real life we don't have like constant arrivals every hour on the ward. Also, there are no overnight departures on this simulator. And the users are able to adjust the proportion of long stay patients. So if they say, if we try to reduce the number of long stay patients on the ward, how would that impact our outcome? The simulator will produce some outputs, including the average number of arrivals throughout the duration of the simulation, the average length of stay for long stay and short stay patients, and also the average queue time for beds. So this is how it looks like. It's the interface is built on Streamlit to make it a bit more user friendly for the users. So the parameters that the user can fine tune include the total number of beds in the ward, the average length of stay, and also the percentage of long stay patients. If they want to, they could make some more advanced adjustments and say, how long do they want the simulation to run for, or how many cycles they want to run. On the result pane, they will see then, firstly, an animation pane that shows how patients flow in and out of the ward visually. They will also get a summary page with all these sort of outcome of the runs at the bottom. Can't see it very clearly on the screen, but I will show the actual sort of demonstration in the breakout room later. So sometimes they want to know, so we know the baseline measures, and what if we increase the number of beds by 1, how is it going to affect the outcome? And with this simulation, they will see then a comparison, a side-by-side comparison. Scenario 2 is basically if they increase the number of beds by 1, what they would get as a result. So we can see here the number of beds increased by 1, and then it seems to be on the timer.
Oh yeah, so if you're happy to wrap up, but have you got many more slides?
Yeah, just reaching the end. So it provides side-by-side sort of comparison when the simulations are run more than once. So the user could then see the comparison between each of the scenarios. Ideas for further expansions include the option for manually inputting or uploading hourly arrival rates, seasonality to take into account different days of the week, time of the year, bed utilization rate, separating occupancy of side rooms, and also to include discharge lounge in the simulation. And that's all for me. Thank you.
Fantastic, thank you, Ray. I think you'll have a lot of interest in that because it's a really nice, generalizable, reusable model for people. So Ray will be in room 1 after this session. I will hand us now over to Amaia and Sean.
Awesome. I will try and share this. Has that come through?
Yeah, can see it now. Cool. Hi, I'm Amaia, that's Sean. We're both from the NHS England Data Science and Applied AI team, and we were working with the waiting list minimum data set. So particularly focusing on single versus multiple pathways. So if you can see in that diagram down there, single pathways are basically just people that are on a waiting list, one waiting list at a time, and multiple pathways are when they are on potentially multiple waiting lists overlapping with each other. So they go on one waiting list, and whilst they're still on that waiting list, they get referred to another waiting list, and so they are concurrent. We decided in this project to do a series of proofs of concepts of data science modeling techniques rather than focusing on one. So we could test out a few techniques, and then teams within our organization could potentially choose to expand on that and see which ones are the most useful. Next slide, please.
Yeah, sure. So talk a little bit about the data wrangling. So as Amaia said, we were working with this waiting list data set. So this was this contains open referrals for patients and their pathways. And we've got this from weekly data from about July 2021. How we approached this is we applied like a set of processing and cleaning and filtering, etc. And the idea is that we retained patient and treatment area information. We generate these outputs, which gives us an overview of who are these patients, and then it splits that into, are these patients that have like a single referral ongoing, or do they have these multiple ones? And we have these assets then to be able to use in the modeling. To just cover some of the challenges we had, probably happens to everybody on these projects, we had a big issue around data access in the first place. And then also the quality of that data and trying to figure out kind of the logic of processing to get these kind of discrete sets for the pathways. So some quick overviews. We had a look at patient clustering. So we were trying to identify cohorts from these assets. We ended up with roughly 3 clusters, which essentially are split into all males over 41, all females over 41, and then this final cluster, which looks at mixed genders, and they tend to be younger. And there's a bit more of a representation from lower IND scores, and also like a mix of ethnic backgrounds. And we're able to see that the kind of ratio of single and multiple clusters across these changes and is slightly different. We also looked at forecasting. So the idea here is that we were like, oh, can we actually see how single versus multiple might change over time? And what we're able to do using a profit model was basically look, if we look at a 12-week forecast, can we try and understand how this might change? With the idea being that because multiple pathways often have an associated or an increased burden associated with them, it might give an idea around resource or demand kind of allocation.
Then we also tested out some binary classifiers, so seeing if we can predict classes of patients that are more likely to end up on multiple pathways, whether that's because of their actual patient features or their kind of initial treatment function code that they were first referred to. So we tested 3 different binary classifiers. The best one was XGBoost. Still not fantastic result, as you can see there. But we've set up a code base that means that you can build on this really easily and kind of iteratively improve. And if you come to our breakout room, we've got some more kind of insight on for the work and reasons why some of this might not have worked as well as we'd liked. That's us done.
Fantastic, thank you both. And Amaia and Sean will be in room 2 after this. Do go and say hi, because I get the feeling there's lots more interesting things that you will hear in that room. So brilliant. Next, we are going to go on to population segmentation with Rhianna and James.
James, are you good to? Oh yeah, perfect. It's just Loading. Brilliant, thanks. So hi everyone, I'm Rhianna. I'm a senior intelligence analyst in the Dorset Intelligence and Insight Service, DICE.
Hello, I'm James. I'm a Principal Research Officer working at Dorset Council, and our project is on segmenting Dorset's population for better health planning.
So we all know that sort of healthcare services are under pressure. We've got ageing populations, chronic conditions, and also kind of limited budgets and resources as well to deal with. And there's a wide range of needs across the population. So by segmenting the population based on sort of health characteristics and also other demographics, the kind of aim for us was to better understand the needs of the population, and also that then enable us to design more targeted interventions.
We started by exploring the data available in our DICE data warehouse. This brings together pseudonymized primary care records with secondary care data, as well as other data sources for patients registered with a GP in Dorset, and that is around 830,000 people. The health data covers things like primary care appointments and emergency admissions and a lot else. It also includes demographic data to add further context. Instead of telling the model what to look for, we used an unsupervised method called k-means clustering. And this let the data speak for itself, revealing natural groupings in the population.
So in the end, we identified 7 distinct clusters, each with its own health profile. We did this using a hierarchical method. So we initially split into 3 clusters, and then from those we further split to end up with 7 clusters. The initial 3 clusters included one with a median age of 35, and then the other 2 clusters had a slightly older median age, so they were both 71. And then by breaking those 3 clusters down further, we were able to get a more detailed picture of healthcare use.
Generally, the younger clusters had lower healthcare use, but a small proportion showed high levels of activity. For example, A2 had higher average primary care appointments and outpatients appointments than A1 and A3. At the older end of the age range, we found 4 clusters with healthcare activity ranging from low to high. This complexity highlights the value of segmentation in uncovering hidden patterns within the population.
So in summary, sort of the segmentation allows us to better understand the population. It will help to design more targeted health interventions, making the limited resources we have go further. And the plan is for our clusters to also support forecasting to help planners anticipate future needs. This kind of data-driven insight can lead to more effective, equitable healthcare. And going forward, we plan to refine our clusters a bit more and explore how they can be used in predictive models. Thank you.
Fantastic, thanks very much. So you guys will be in room 3. Please do head in and have a chat with those as well. I think, you know, it's more really widely applicable work, you know, some fantastic stuff that could be reused across multiple organisations. So finally, in our lightning talk segment, we have Jake talking to us about length of stay.
Right, could you let me know you can see this all right?
Yeah, that's coming through, thanks.
Right, hi everyone, I'm Jake. My project's on understanding the drivers and length of stay. So just to understand what the motivation behind this is, length of stay is the number of overnight days a patient spends in a hospital bed when they're admitted. In North Central London, we observed a trend where length of stay had increased over the last 5 years, but we weren't sure why. So the project was to make a machine learning model, understand what features correlate with length of stay, and then use that to see if we can explain why we had an increase in length of stay. This is a distribution of length of stay in North Central London. So the key takeaway here is that length of stay is heavily populated around 0 length of stay and 1 length of stay. And then there's a massive drop off as the length of stay increases. To start this project, I looked at existing research papers. The main takeaway from them was that there is a consensus that modeling length of stay is notoriously difficult and complex problem to solve. The other benefit from it was I was able to use it as a starting point to figure out what features I could use in my model to get a head start. And then it also gave me some insight into what sort regression models I could use for the project. So just to talk about what model I ended up with, I originally started trying to do an all-in-one model with a lot of bells and whistles. However, that didn't work out too well because I think it was a bit too complicated. So I'm now working with a much simpler model, but it's built on top of a much more robust Python pipeline, which can then be further developed more easily. So the current features are age, gender, and emergency admissions. The other major change I made was I made one model per major hospital site because the type of performance delivered by each hospital site was quite varied and it didn't make sense to put them in the same model. I also alternated between using Poisson and random forest regressors to see which had better performance. There's also a diagram of my Python pipeline showing that data goes from the data source all the way to the outputs of generating the models and tracking various performance metrics. Just to talk about some of the performance metrics, I did root mean squared for all of the site models. The variation here shows it was a good idea to split them in the different sites into different models because some of the more specialized sites have quite varied root mean squared error. There was also an attempt to plot the actual length of stay against predicted. Ideally, you want the dots to be along the red line, but that's not quite the case here because the model still needs to be improved. So that's something to work on going forward. And then here is some of the key reflections that I had, but I'll end the talk here.
Fantastic, thank you, Jake. I think it's really, as you say, such a complex, thorny problem, and I imagine there'll be lots of people who would like to come and chat a bit more about it because it is something that can have such a huge impact on the ability to plan. So fantastic. I shall stop that timer. So we are now going to open up the breakout rooms again, if I can keep track of all my different Zoom windows. So Ray in room 1, Amaia and Sean in room 2, Rhianna and James in room 3, Jake in room 4. Please feel free to move around between the different rooms. Breakout room bar will hopefully appear in just a second at the bottom of your Zoom window. If it doesn't, check under the 3 dots and the more icon, it should be in there. And I'll be hanging around in this room to help you on your way if you are having any difficulties with Zoom. So please go and talk to our lovely HSMAs about their fantastic project work.